Welcome. My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar, which will be presented by MGgrafeno and by Luis Cansado. Thank you, Luis, and I appreciate you being here and presenting and sharing with us. And so, as the Graphene Council, we are hosting today's webinar. We're very happy to be active in Brazil and in Latin America through our partnership with the Mackenzie Presbyterian University. And we're very pleased to have MGgrafeno as one of our valued members in the Graphene Council, a leading institution in this field. The Graphene Council is the largest community in the world for graphene-related professionals, both academics and in the commercial side, connecting more than 30,000 material scientists worldwide. The Graphene Council represents the entire ecosystem. So we have universities, we have graphene producers, we have intermediary companies, and we have important end user companies like Ford Motor Company, BASF, Vittoria Bicycles, and many other end user companies. One of the reasons why graphene has attracted just so much attention and will continue to attract enormous commercial attention over these next years is because it's such a versatile material that can be applied to so many different applications for different attributes, whether that be for its electrical conductivity, its thermal conductivity, its inherent strength, or a combination of all of these factors and other characteristics of graphene, which are so important and why it's being widely used. The Graphene Council recently conducted a global survey of the graphene sector, and we received more than 800 replies to our survey, 1/3 of which came from academics and 2/3 came from commercial professionals representing producers, buyers, users, application developers of this graphene material. And we have the high-level results of this survey are publicly available. So if you wish to have a copy, if you haven't already seen the report, which was just published in January of this year, please reach out to us and we'll be happy to send you a complimentary PDF copy that you can review. And so these are my contact details. We will send this out to you after today's webinar so that you'll have that information if you would like to engage with us, if you're not already a member of the Graphene Council. And we have some additional resources listed here, including an article that was published in Nature, talking about the commercial development of graphene that was authored by us. And then we also have quite a library of videos on different aspects of graphene use and characterization on our YouTube channel. And then, of course, our website has a lot of information. So with that short introduction, I now want to turn this over to Luis, and we will now receive some information about the important work that MGgrafeno is doing. It's a unique entity in Brazil because it's a collaboration between different stakeholders, and it's an important, I'd say, force in Brazil that's going to help spearhead the commercialization of graphene materials. So with that, Luis, go ahead and take over the screen if you like. And it's all yours.
Okay, thank you very much, Terence. Thank you for this invitation. Thank you for the Graphene Council. This is a great opportunity for me and for our colleagues here from the MGgrafene project to show our developments. And my focus today will be on the methodological framework that we have developed for quality control of liquid exfoliated graphene. Of course, many of these subjects and then techniques that I will show today and the approach that I will show today can be extended to other systems, of course. Okay, these are the principal investigators. We have two members of the CDTN, Dr. Adelina and Placidia. We have the professors from the Federal University of Minas Gerais, Flávio, myself, Omar, and Bernardo. We have a professor from the State University of São Paulo, and Valdirene from Codenge, which is the company, the economic development company of the state of Minas Gerais. This is the university, the university campus, okay? let me point here. This is the physics department around here. And this is the CDTN. This is our nuclear facility. And the graphene, the MGgrafeno project is a joint project between these two stakeholders and the CODENGE, who is the financial support. This is, for those who don't know, Belo Horizonte, Brazil. Okay, we are located at the state of Minas Gerais, at the southeast of a part of Brazil. This is São Paulo, Rio, and Minas Gerais, and the Espírito Santo. This is the southeast region. People may know this stadium. This is the Mineirão Stadium, okay, where we had that game, that match against Germany. So we became something like some sort of tourist place for soccer lovers. Okay, let's talk about graphene. This is the MGgrafeno project. 62 members, 22 PhDs. I already talked about the institutions. We have CDTN, the physics in UFMG, the computer science, very important. We have an excellent microscopy center that makes our eye life easy. And we have the State University at the Metallurgy and Materials Department. Okay, in terms of numbers, we have already 4 years of projects. Okay, we have something around 10% of conversion graphite graphene. We have installed a capacity of 300 kilograms a year. Okay, for nanographite, it means the very thin graphite that is separated from graphene at the end. We can make like 2.6 tons years, okay? We don't have any residue that is discarded. Everything is recycled, so we don't waste water. And a very important part of our work is the quality control. This is what I will talk about today, okay? So it's important to understand that the best graphene is not the most beautiful graphene ever, right? So commercial graphene, there's a lot of materials that can be called graphene, and it's not obvious that the most beautiful and the defect-free and larger graphene is the best for your application. So what is important, okay, is what's your target? And if your graphene makes your target match with your target, okay? So understanding, okay, and provide accurate information about the properties that make the graphene suitable for the target application. This is our goal. Okay? This is our true goal. We don't want to show beautiful graphene. We just want to show the real graphene, and to people understand if that graphene is suitable for application. If it's not, we work with the graphene to make it suitable. But what we want really show is accuracy in our measurements. Okay, so this is somehow some microscopy, electron microscopy, high resolution transmission electron microscopy images of some of our graphene. Okay, of course this is one piece of graphene, very large, 1 micron for LPE graphene. This is quite large. And you may ask if, so this is like 4 layers, you can see here. You may ask if I took this beautiful graphene from a bunch of small graphene. I say, of course, yes, because I want to show a beautiful graphene here. These are the graphene nanoplatelets. We call graphene nanoplatelets 5 to 10 layers, okay? And we have the nanographite. This is the basis that we do. We are now customizing these materials to serve the industry, the local industry or the external industry for many applications. So the aim of this project now at this point is to find partners and applications for the graphene that we produce today. Okay, our characterization matrix follows pretty much what ISO has presented in the documents. We have some techniques that pretty much everybody use, like microscopy, electron microscopy, UV visible spectrometry, atomic force microscopy. This is very important. Gravimetry, X-ray fluorescence, Raman, dynamic light scattering, and X-ray diffraction. So we measure different properties. Okay, we have all these equipments on site, and we also have some different techniques that I will show here, and methods for analysis, which is very important. Just measuring is not really the most difficult part. The most difficult part is to extract the right information, as I will show. And we also have some new techniques which are not commercially available, which we are applying in our systems. Okay, I will start my technical presentation here with one example, which is our fuel layer graphene. Okay, we call this like less than 5 layers. And here's the typical Raman spectrum of the fuel layer graphene. This is the inelastic light scattering, for those who don't know. And there is something very peculiar with this. This is people who work with graphene appreciate this technique very much for 2 reasons. Okay, 2 basic reasons. There are many reasons, but I'll tell you the basics. This peak here measures the amount of defects that your graphene have. Okay, so we can estimate the defect density by the amplitude of this peak here, or the area of this peak here. And the shape of this another band here, which is called 2D band, gives you somehow the number of layers, like the number of, it changes with the number of layers. We can see here for reference samples, okay? Reference samples, I call reference samples the Scotch tape graphene that we make on top of silicon, okay? Like the Nobel Prize. For 1 layer, it looks like a single Lorentzian peak, and for 2 layers, it changes, and 3, 4, 5, 6, 7. It changes a lot if you change the number of layers. And this is because the electron funnel structure changes with the number of layers at this scale, okay? And this is very useful. I will show why. So this is the dynamic light scattering, which gives you some kind of hydrodynamic diameter. And this is the thermogravimetric analysis, which is quite accurate to give you the amount of graphene that you have, the carbon material at least, and the amount of residue that you may have in your system. Okay, if I look at this picture here, okay, I just measure this from the liquids, from the solution. Okay, the suspension. I would say that this peak here gives me something around 4 to 5 layers. Okay, this is what I would say about the shape of this peak, and I would say that my diameter, the diameter of my graphene is around 300 nanometers. Okay, so this is what I already showed. This is a beautiful TEM picture of a nice, very nice flake. Of course, this is the nicest I could find. If I search more, I could find better, but this is the best I could find because I want to show the beautiful. But we have to make it different. Like this is what we do. This is what we developed. We developed a system that we make sample preparation. We work a lot on sample preparation, and we make AFM analysis, and we have like here something around at between 10,000, 15,000 flakes. Okay, we cannot see them, but our automatic analysis system can see them. Okay, and then we have the number of layers as a function of the lateral size that we can measure, and we have really statistical measurements. Here we can make these histograms, okay, of number of layers and lateral size. And for this sample here, we measure like 9,000 flakes. And we have all the statistics about how many flakes are between 1 and 5 layers or 6, 10 layers and so on. So another example is here. Okay, we have a non-centrifuged graphene that just came out of the plant. And we have a centrifuged graphene. We see that we get rid of a lot of big flakes here. Okay, and we make this AFM analysis and we measure. Okay, and we see here this is non-centrifuged. This is number of layers as a function of lateral size, and we see that we get rid of a lot of flakes here. Okay. They have a lot of layers, so this is graphite. So they have like something like 50 layers or more. And they have like a 1 micron size. And then the centrifugation just cut this here, okay? But if you look at the statistic of numbers, it doesn't change much. It means if somebody show you, if somebody has this graphene and show you the histogram for lateral size of or number of layers, it looks very much the same as if you have this graphene here. So what's the problem with these measurements? Because they are really statistical measurements. So why they look so? But they're completely different materials. We can see here, and they look so much alike each other. So the problem here is in these numbers that you have statistic of number, area, and volume. If you look at the statistic of numbers, which is pretty much what everybody does, or almost everybody does, you don't see many difference. Okay, so this is translating this in this chart here. We have the percentage of each type of graphene, like the purple is 1 to 5 layers, the green is 6 to 10, and the gray is like a graphite, okay? We see that in terms of numbers, we have a lot of graphene particles, okay, for both samples, and they look very much alike, but they're not the same. We can see here, well, from the AFM images, we can see that they are not the same. So let's switch here to the area statistics, okay? We see if you take the area of the flakes into consideration, for this sample here, more than almost like 65% of the area, okay, is composed by graphite. In this case here, is something around 10%. So, okay, area is something that really translates what we are seeing here. Okay, this is the real statistics that shows what we are seeing here. But there's another dimension here, which we are not seeing from this image, which is the volume. If we take the volume statistics, okay, which is really what you are buying, if you buy this sample here, you are buying 90% graphite. If you buy this sample, you are buying 20% graphite in mass, in terms of mass, okay? So they look very much the same, depends on the numbers that you show, okay? If you show the statistic of numbers, if somebody show you statistic of numbers of flakes, okay, it means nothing, okay? The amount of graphite is very small because you have like a very few flakes and you have very many tiny graphene flakes, okay? You have to see this one here, or at least the area, okay? The statistics of area. All right, so this is the same pair of samples. Look at number, area, or mass, okay? And another thing, truly statistics is something more than 10,000. We have tested this a lot, and we know. Let's go back to the dynamic like scattering or the Raman. Okay, if you take this was taken from this sample, the non-centrifuged sample. Okay, the dynamics like scattering shows something around 300 nanometers, and the Raman show you 4 layers. This is the sweetest spot as possible that you can get in this chart. It's the best compromise between small number of layers and large size, okay? And this is what these two techniques gives to you. And this is what everybody shows, okay? Nobody wants to show the truly statistics, or it's not that nobody wants to show. It's difficult to get the truly statistics, I understand that. People don't know that this is like this. I'm not saying that people is unfair. It's just a matter of ignorance. So people take the techniques that just give some numbers, okay, and assume that that is true for some kind of average number of particles, which is absolutely not true, okay, it depends on what you're looking for. So, of course, this is not made by human hands. We cannot analyze 10,000 flakes. We don't have power force for that. But we have a lot of brain in the computer science department to make our life easy. So this is all automatic, okay? This has been tested by some peer people around the world, and they really understand what we are doing, and they know that this is very robust, okay? The statistic is real. We have a lot of automatic image treatment, and this is tested at the limit, okay? And this really works well. All right, so with these statistics in hand, we have some sort of different approaches that we can make, but this is just one showing here that we can make all these charts. For example, the square root of area as a function of the height, okay? We measure different materials as an example. For example, this is talc, and this is graphene, and we show, okay, that this number is quite interesting, the aspect ratio between the average lateral size and the height, okay? And this is what we call the R ratio. And we show that different materials give you different statistics, okay? This is based on like between 10,000 and 15,000 of flakes. And we have, if we get the logarithm of these distributions, okay, we have a very accurate information about our system, okay? This is explained in this paper. And we see here that we make these samples at exactly the same procedure, okay? And they are different, and we can see here. If you just look at the data, you don't see much. It's hard to extract the information, but we can see here. Centrifugation, okay? We measure a lot of graphene, we get the parent sample, okay? And we do different centrifugation, like 5,000 kg, 10,000. We just get rid of the big graphene. This is the lateral size as a function of the height. Always working with the logarithm here, make our lives easier, okay? And we can see here how the certificate. So this is the parent sample, and this is the like a 17 kg sample, and how it goes down, okay? So centrifugation decreases the aspect ratio between A and H, okay? We can see from the center of the Gaussians here how this is decreased, okay, as if you increase the acceleration. So this type of information was impossible to be gathered before we developed this type of automatic analysis. As I said, we are in contact with a lot of scientists, peer people in this area, and they really appreciate the power of this type of approach. Another thing, this was really surprise. If you doing this type of analysis, okay, we can plot also another type of ratio, which is the ratio between the major, okay, length and the minor length, okay, and of course you can make like a lot of statistics here, but the main point, okay, is that this ratio get like larger if you make the centrifugation. In other words, the centrifugation causes some kind of elongation in your graphene particles. More elongated particles comes if you increase the acceleration, okay? This was already somehow guessed by some peer in the area, but nobody never really had this type of information before. So this is just another example, okay, of some kind of information that we can assess with this type of technique that nobody ever was able to see before. Okay, I will get back to the Raman. I already told you there are some famous papers showing that that 2D band changes with the number of layers. This is kind of changing the number of layers. And we start to use this spectroscopic technique to measure the number of layers of graphene. This is very common for those who work with graphene characterization. And here what we did, we characterized a lot of Scotch tape graphene, okay? And we made like Raman maps, AFM, okay? And we built a group of something around 100 pieces of graphene from standard samples, the Scotch tape samples. And we measure a lot of 1 layer, 2 layers, 3 layers, and we built, okay, a library of this type of standard samples. And we did something that is called principal component analysis, okay, which is basically a software that takes some mathematical approach, okay, to extract the main component analysis spectral components of these curves here, okay, and our analysis showed that this band, okay, what is seen here, okay, can be very much mapped in something, in a phase space that we call the two main principal components, okay, PC1 and PC2, and they just project in some parts of this chart. So 1 layer projects here, 2 layers project here, 3 layers, 4 layers, 5, and these are the standard samples that we have, okay? All right, so we built this standard PCA phase space, okay? The problem here is that our brain can differentiate very much these peaks here, but it's not easy to make like some sort of fitting procedure, okay? That makes clear, like mathematically clear, what's 1, 2, or 3, or 4 here. So we use this PCA analysis and we build this standard space. And now we measure our graphene. The same samples that we measure the AFM, we do Raman map, okay? And we also measure like thousands of Raman spectra. And we do the PCA analysis. We call it standardized PCA analysis because we project our graphene in our standard PCA space, okay? And we see the distribution. So we see like from 2 to 4 layers. We have many layer graphene from like a 6 to 10. So we say, okay, this is like more 5 and more graphite, okay? But the problem is that this is not accurate. We start to see that we have, for the AFM, okay, we see a lot of thick layers. This is number of layers, and this is the histogram. We have a lot of thick layers here, but the Raman just don't see them, okay? We miss them by Raman. And then these are different samples. We see here a lot of thick pieces, okay? And the Raman gives you the difference, some kind of difference, but is not as accurate as the AFM, at least for this technique here. So the problem is Raman see stacking. Yeah, that's true. The Raman is sensitive to the stacking, yes. But these graphene pieces, they are not really nicely stacked, okay? What Raman sees is the electronic and the vibrational structure of your system. If the system is loose, somehow, it's okay, it is still tight, okay? But it's not completely loosed, okay? The Raman will see them as like a monolayers or bilayers, but they are still together, okay? For example, if you take a very nice pile of paper from the pack, okay, it's perfectly stacked. Let's suppose you just messed up with this with something, like you put water or you just smash, okay? You may have that thing together, but they are not nicely stacked, okay? So the Raman somehow will tell you that that thing is graphene, but you still have some kind of, they are tied to each other, but the Raman you say that this is graphene, okay? For example, if this is like 2 layers, if I have 2 layers here and 2 layers here, Raman will tell me, okay, this is 2 layers, but I know we have like 4 layers here at least. Okay, so, or you have something like this. Okay, the layers are loosed, so the Raman may tell you that this is graphene, but it's not really graphene because they are still together. So we adopt another approach, which is the G-band intensity, which just measures the intensity, okay? And we compare with the substrate intensity. And we can see here that this peak from graphene increases the ratio between the peak and the silicon peak from the substrate. The ratio increases as I increase the number of layers, so it scales nicely with the number of layers. And then we make some standard measurements again, and then we measure the G-band intensity, and we can reproduce, okay, much better the AFM measurements. So in this case, the Raman communicates nicely with the AFM, okay? And what we call this is like the data from the 2D band is not waste, okay? It tells you how much of your planes are uncoupled, okay? So they may behave, the electronic structure may behave like a 2 to 4 layers graphene, but if you measure the flakes, okay, they're still tied together, okay? And this is what you may have like morphologically. Let's put like this. So we developed this. We also measure like thousands of flakes at once. We make Raman map. It takes like a few hours, but we have an automatic system, and we are developing a deep learning based denoise system, which improves a lot the spectrum shape and makes this analysis very smooth. Okay, this is the bare data, and this is the denoised data, okay, which we are developing with the computer science department. This work is already published in Carbon, but we, for more focus in this deep learning denoise, there's another manuscript in preparation. We also can measure defect density. Our graphene is like this. We have like boundaries, we have point defects, And as I mentioned, the ratio between this defective band and another band in graphene gives to us some sort of distribution about the defects that we can understand. If we have more defects, for example, in this chart here, if we go in this trajectory here, we have more defects, like a point defects. If we go in this trajectory here, we have more boundary defects, okay? And this is basically the ratio between these two bands or the width of this G band. This is all explained in this paper if you want to know more about this. And we have simulations that give us some kind of mixed material like this, which might be the reality, okay? And this is also automatic. We have the RAM analysis system. We don't do these things by hands. This is like a daily development, okay? All right, so, and now we reach to the point that we are making some feedback system for total quality control. We already know how these things work. If we go to the tabletop measurements, like for the lab, if we take our graphene, we deposit our graphene in a silicon substrate, we measure the AFM, the Raman, we get all this data. We are working with machine learning to understand how this disconnect to the spectrum that I show at the beginning that we just measure from your suspension, okay? If you measure your suspension, you get this. How does this connect to all this information? There's a lot of machine learning that we can tell us this. And our aim, our goal here is to learn, okay, or making the machines learn how they translate all this information to a single spectrum, and we get the single spectrum directly from the pilot plant. So we have an automation system called G-Scan that measures Raman spectrum of the circulating graphene system in our pilot plant. Okay, and we are doing all this machine learning processing to understand. And well, at the end, if we succeed, which I believe we will do, we can adjust, okay, the process parameters, like, okay, decrease the temperature, increase the okay, it's too basic, it's too acid. Increase the power of the plant, increase the flow, decrease the flow, change this chemistry, or so on, by doing some feedback system with Raman, and we may also apply other type of spectroscopy here. Okay, we also have some kind of instrumentation in parallel in our nanospectroscopy lab. This is a joint project with eMetro. We developed this Raman nanoscope to measure things at the nanoscale for Raman, and this is called tip-enhanced Raman. And the main problem here that we want to address is that I show you the powerful how Raman spectroscopy can give you nice information about the graphene. Okay, but the problem is that we have some serious problem with the spatial resolution. As many of you may know, for like half of wavelength of light, we don't have spatial resolution. For example, for visible light, the wavelength is around 500 nanometers, and below 200 nanometers, the optical microscopes don't really work well, okay? This is called AB principle. You cannot, okay, resolve two-point sources which are closer than a distance which is the wavelength of light over roughly 2, okay? But what we do, we just approach an optical antenna which we developed here. This is a gold pyramide, where we have some kind of plasmon confinement here. This is an optical antenna which we approach to our system, and we make the Raman signal enhance a lot, and we get the spatial resolution, which is defined by the size of the tip, okay, the apex, which is somehow between 10 and 20 nanometers, okay? This is just an example. This is the confocal image of a graphene, where people at Inmetro make with ion bombardment the Inmetro logo. For those who don't know, Inmetro is our standard bureau, okay, like a NIST or NPL. This is our standard bureau, and people made some graphene with defective, the Metro logo, and we measure the confocal Raman of the logo. Because this is so small, we don't have optical spatial resolution to see the logo, but if we do the tip enhanced, okay, we can see the logo nicely. Okay, this is the gain of optical resolution. And why I'm doing this, okay? So that all the technical aspects, this is not commercially available, but this instrument is being developed we have, in April, we will have the first commercial prototype, okay? This is a startup here at the university. And we have all this instrumentation with the small probes. And here's the thing. We already measure some graphene from the MGgrafeno projects and other graphenes also, okay? And we measure the amount of defects. And there are a lot of new metrics, okay, involved here. If you're interested, you can read this paper. But here's the thing. If you want to analyze by Raman just one flake, okay, it's blurred like this, okay? Because we don't have spatial resolution, okay? But with AFM, we see the flake. The flake has a lot of structures. It may have some kind of chemistry attached. It's not just like a single nice uniform flake. So we can do this nano Raman, okay, and we improve a lot the spatial resolution, and we can take like hundreds of spectrum inside of the flake and analyze the flake locally, okay? This is completely different. So we are now analyzing the flakes, the chemistry, the functionalization, and so on. This is another example, okay? This is a software that we developed for the NanoRama. This is a lot of graphene flakes, but this is like 150 nanometers by 150 nanometers. This would be completely blurred, okay? The size of the laser spot in a conventional system is like 3 times this image here, but we have a lot of information about the defects, local defects, the number of layers. We see that there are a lot of different number of layers inside of 150 nanometers, okay? Here we have a small number of layers, we have large number of layers. We see that we have more defects where we have low number of layers. This is correlated somehow. And we are doing all these developments. Now we have some chemistry involved that we can make like local analysis in our flakes, okay? And this is under development, and soon people will see how this technique can resolve a lot of problems or can at least raise some questions, okay? This is just a kind of advertisement of how this technique can be really powerful and nice. We measure the twisted bilayer graphene, and we could see the crystallographic lattice of the twisted bilayer graphene with Raman, which was something really, really amazing. And this was the cover of the Nature 2 weeks ago, just showing how this technique can really, really make like new things and open new paths. Okay, just closing, it's very important that we have a system for analyzing everything. We are also developing this, actually the computer science guys, they're developing a system that measure, make big data, control people, process, everything is controlled by the MGgrafeno smart system. This is how we call it. Standardization, we are working with in Metro. We have a lot of standard information. We know that we can improve the standards. We want to make this available. We understand that the robust development of the area must have good standardization, accurate measurements, accurate protocols, and we hope we can provide or at least contribute to the world with our experience here in Brazil. So this is the path. Of course, there are a lot of partners here in Brazil, and we hope we can have also partners soon from ISO. Of course, we call with NPL. We are involved in this Interlab and so on. Okay, so I came to the end. Thank you very much, and I will be glad to answer questions if you have.
Excellent. Luis, thank you so much. This is Terrence. So that's a fantastic presentation, and I think this is really, really significant development that you are working on, that I hope that the significance of it is not lost on graphene producers. In particular, what we've seen from a recent survey was the ability to do quality control batch to batch or in production line, as you show, is one of the most important and also one of the most difficult things to do. As you likely well know, there is a standard coming out from ISO that should be published this week or next, specifically on characterization methodology for graphene materials. And these standards are important and needed, but in many cases, they're more suited for, let's say, preparing data sheets, taking sample size, not really for quality control in a production setting because of how long they take, how expensive it is to do, etc. So I have a bunch of questions for you about your presentation. I'm very excited about this. But let me go to the audience's questions first. From Lucas Fashin. I'll try to read the question and see if this makes sense. The mass percentage distribution is calculated based on area times the number of layers, right? That's the question. Is that the mass percentage distribution, is it calculated based on the area times the number of layers?
Yeah. This is exactly. We take each flake, we measure the area, and we calculate by the number of layers.
Okay. So the answer is yes, right? To that.
Yeah, the yes is yes.
Okay. So another question that comes in about how to measure the surface area. So this is Rodrigo Vasconcelos, and I'm sorry if I mispronounce anybody's name, but are you using BET? How are you measuring the surface area? Is that BET, or are you calculating surface area by doing lateral size dimensions like with AFM or some other technique?
Well, we measure the AFM. This is what we have really well established now. Okay. And we also are under development for another spectroscopic process, okay, which I'll be glad to show in near future, okay. We have another spectroscopic way to measure the surface area, but right now this is AFM, okay. Everything I show now for area, surface area, was made by AFM, okay. BET is quite complicated. We don't use BET. We have another way to make it spectroscopically, which I will show soon. Okay, but right now is the AFM, which is our way to show the area.
Well, maybe not to spend too much time on BET, but I have a couple of comments and would like to get your response. So speaking with some other metrology labs, the comments about BET is that it's not quite accurate enough or reliable enough. It depends how you prepare the material. And from the commercial side, I have seen graphene companies that have relied on BET to measure surface area and then extrapolated that to say, okay, we have 2-layer or 3-layer material based on the surface area, which I believe is very unreliable, but I'd be curious to get your opinion on that.
Yeah. So the BET, the problem with the BET is that it is based on a very complicated mathematical, calculation. Okay, it's a model. It's not a direct measurement. So so basically, it's absolutely indirect. Okay, so and the different results that you can get if you miss something in the model, or if your system doesn't behave as the way you suppose. So you have to make a lot of you have to suppose a lot of things, and depending on what you suppose, okay, you get completely different results. Okay, it can be like 1 layer or 1,000. Okay, this is like the error bar. So I don't think BET is like a realistic for measuring all the systems, but I do appreciate the effort of people who work with this. I know this is serious. Okay, I'm not saying that everything is not accurate or everything is wrong. I know that's like a serious science and serious technology, but really, it really depends on the model. It really depends on a lot of guess. Okay, and I would prefer to make direct measurements as AFM, or we can develop other things. Okay, I think we have to choose and develop new pathways to do this.
Understood.
That's my opinion.
Thank you for that. So one of the questions relates to AFM, which of course is a very precise technique. And the question is very relevant, I think, because the question is about sample preparation for AFM. And before you respond to that, I would say there is a good practice guide that came out from NPL, which I don't know if you want to comment on that as well, but can you just speak a little bit about the importance of sample preparation for the AFM side, and also if you have any guidance on sample preparation for AFM?
Yeah. Okay, this is a very good question. Okay, because this is absolutely crucial. Okay, what's the problem with the sample preparation for AFM? If you don't prepare it nicely, you may get rid of some sort of type of flakes. Okay, small flakes can get rid because the liquid just wash them, or you can get rid of large flakes because the liquid just shrinks and get the large flakes to the center, so people measure what is outside, which is just the smaller flakes. So you have all these superficial forces which are very strong at this scale. Okay, so it makes the whole difference. So we spend like year time, some kind of year time, trying to figure out a good way to prepare the samples, and we came with this functionalization, which is the APTES, and also temperature is very important, and the density, the mass density is also important. So it's not just like a drop and let it dry. We make some functionalization at the substrate. We drop, we make some temperature, and of course, this, as I said, everything goes better and better every day. Okay, but you can make a good sample preparation if you get these papers, which I let me show here, give you the reference. We are explaining there. We don't hide results because we want the graphene to be developed. We understand that characterization is something that can really push the area to be improved. We want the graphenes to be, the area to be like supported by the industry. So we say the truth in our papers, and we provide the real information. You can access the information here. We have their sample preparation details, okay?
Mhm.
And this procedure that we use was tested by colleagues in Europe who work with graphene, like important people, can assure you, like a peer people in the area, and they really appreciate the way we do it.
Well,
So it is really important, and the details are here.
So Luis, I think you guys have a real breakthrough with this technique, and I'll share some additional questions that I have. So for example, with AFM, as you mentioned, you have a problem with selection bias, right? So if you're doing individual, right, people can pick which flakes they want to characterize. The other problem, of course, is even with 10,000 flakes or 1,000 flakes, it's still, relatively speaking, from the total amount of material, an extremely small sample size. But what you're doing is a step change improvement because of the number of flakes that are actually being read. But I found it really fascinating. We have big problems with specification sheets for material. We're talking now from the commercialization aspect. And we'll have people who claim, okay, our material is 6 to 9 layer material, graphene material, but they don't give a distribution, right? So they don't talk about what percentage of flakes are maybe sub 6, how many are between 6 and 9, how many are above 10, for example. And then what I found really fascinating, exactly the slide you have up here, was the difference between a statistical number based on flake size, and then you have the difference between them based on area, and then based on mass. Now, one question so first of all, I think that alone is a great advancement, and then having the distribution within that is in my opinion, is something we should think of as a standard requirement for specification sheets, so you can really measure and compare material one to the other. What is your opinion? Because one is measuring surface area or lateral size versus mass. And often with graphene, especially because of surface chemistry and the aspect ratio, seems to be a really important factor in how the graphene performs rather than mass. Do you think mass is more important, or do you think surface area is more important for the actual performance of the material?
Oh, this is a very good question. Okay. This is a lot of testing, and my first guess is area. Okay, area is what really matters. And but of course, you can have also something called intercalation, because as I showed you, even if you get a thicker graphene, I think this chart makes it very clear. See how the Raman show you that even if you have a thick graphene, they may have like the sheets are loose, so you may have a lot of intercalation too. But I completely agree with you that the main statistics which we really want to see, because okay, so there are different information here. Let's take, for example, if you have these statistics here, you just know what you're buying. Okay, I'm talking about okay, let me take my pointer here. If you know this mass statistics, you know what you're buying. Okay, I'm buying like the amount of graphene that I'm buying. So this is very important, right? You want to know it. So these statistics here, I think, is more technical. Okay, from the graphene I'm buying, what's really the area which is graphene? Okay, and I think technically this is what matters. I think you're right. It's not this, but is this, okay? This is technically very important. But you also want to know this, okay? Because this gives you like somehow how your graphene is small or large or something. So I think everything here is important. As a buyer, I would really like to see this, okay? As a technical manager or engineer, I really would like to see the area. I think you're right.
Well, it strikes me, of course, we don't have to choose between one or the other. You can, of course, always report both. But
Yes.
I think the challenge then is for because we see end users, even in sophisticated, let's say, chemical companies, technical companies, their understanding of graphene is extremely basic. So if you reported both of those side by side, you would have to educate the end user, the consumer, what that actually means, right? And how it relates to one another, because they might interpret it differently. I have another question for you, Luis, and that relates to the slide that you were just on a moment ago with the Raman scans. If you could go to that. The comment that you had made with the Raman graphs, and the fact that Raman misses a lot of information with stacked material and with some thick material. We've heard that from other expert. Yeah, I think the slide, there you go, exactly. I think we've heard this from some other metrology labs and from other experts in the field that Raman is good, but really has limitations, up to a certain number of layers, and then it becomes unreliable. Likewise, we've had companies that really rely on Raman as their proof, quote unquote, that they have graphene, and also use it to do their distributions and such. And because Raman is relatively quick and relatively easy to do, so I'd like to hear your comment about how much you rely on Raman. And I know that you have now this nano antenna, which sounds fascinating, so you get the better resolution. But if somebody were to question, okay, well, how reliable is this Raman, especially if you have 6 to 10 layer material, how would you respond about reliability?
Yeah, I think first of all, if you want to do Raman as for the AFM, you have to do statistics. Okay, so you have to do the Raman maps, get like thousands of flakes, and take into consideration. People focus a lot on the Raman 2D band. Okay, and this is basically, I know this is sound rough, but people take the specialist and say, okay, let's look at this chart. I make my Raman, how it looks like. Okay, it looks like 6. Okay, and this is what you get. There's no science, okay, that tells you how to fit a 4 layers spectrum. Okay? It's a mess. It gets too complicated. You have something like 16 contributions here. So with 16 contributions, you can fit everything that you want. Okay. So there's no science to tell you how to fit this, and the theory that say, okay, 8 layers, it has this shape. So people look and say, okay, okay, 7, looks like 7. This is better, okay, because this is a computer doing pretty much the same. It just analyzes the shape and say, okay, it drops here, all right? And this is what we do here. This is a computer doing the same, pretty much the same. Look at the shape and say, okay, yeah, it's here is the best. And then, okay, so the 2D band, this is the analysis. And as I told you, is how the layers are coupled. This is not like the actual shape of the flake, okay? Just take like a bunch of sheet, a paper sheet, and this is just all messed around or wet or something. Okay, they may be together, but they're not nicely coupled. Okay, and the Raman just see that, and people take advantage because you at the end you measure a small number of layers because they are together by 2 or by 4. Okay, there's another way, as I show, which is the G band intensity. that you have to make some kind of standard samples with the silicon, and we have to compare this, okay, the intensity, and you may get a protocol, okay, which is somehow reliable, in the meaning that you can get the information from the AFM with Raman, but not the same protocol that people usually do. So this is really not real. Okay, so I would tell you, if I was like a company that has a Raman, okay, in the lab, I would measure and look at the spec and say, okay, this is a 2-layer. Buy my graphene, 2 layers, 3 layers, 4 layers, but this is what the AFM say. It's like 10 layers, 7% in numbers. So this is a lot of mass. This may be like 80% of mass of graphite.
Yeah.
So the spectrum would tell, okay, this is bilayer graphene. So the answer is only the Raman to the band alone is not a reliable way to show the number of layers.
Okay, excellent. There are a bunch more questions, so I appreciate your time. Can you stay with us for just a bit more?
Can I just say something?
Yeah.
It hurts for me because I'm a Raman guy. So I was a Raman guy since I studied like 20 years ago. People know me in the scientific community as a Raman expert, okay? So I'm not happy to say that.
Well, if anything, that means we can trust you when you say and you make a critical analysis of it. I think that's quite helpful. So I have a couple of additional questions, and we have other questions from the audience. So one, you mentioned there are some interesting other measurement techniques like XRD, for example, or DLS, the dynamic light scattering, that you don't really mention, right? And so I wonder how, I mean, you mentioned them at the beginning, but this technique that you have developed looks like this combination of using Raman with AFM and then artificial intelligence or machine learning to do the extrapolation. So where do these other techniques like XRD or DLS, where do they fit into the picture?
Yeah, this is a good question. We have worked a lot with all these techniques. Of course, the techniques that start to give you more response, you tend to focus more, okay? Yeah. The X-ray, I think, is very important. We have also made good progress with the X-ray. And we develop a way to prepare sample preparation, which is it's very important to be very thin, okay? The preparation is very thin, okay? To avoid asymmetry in the peaks. We have this. We have a lot of work on the dynamic light scattering, okay? UVVs also. It's just that I'm not ready to deliver the information very nicely packed as I did today. It's not because I'm hiding, okay? It's just because I'm not ready.
Okay.
No, I was just
curious.
Yeah, we do have this, okay? We are now in a very large effort to put all the information together. So all these techniques, how they connect to Raman. So because we have all this nice AFM, lot of information, how the dynamic light scattering look like, how they compare, how the X-ray. So we are doing this, okay?
Excellent.
We are packing together. Maybe in 6 months or 1 year time, I'll give you the whole package. So it's almost there. It's just that I don't have it nicely packed yet, but yeah, we are getting there.
That's really good news to hear, because that would be quite interesting to see how they kind of cross-check and verify and validate one another. That's excellent. We'll keep up the good work on that. We have a question from Nathan Silva, who's asking about these techniques for measurement and how they might apply to some other materials, which could be something like a graphene oxide, which would be related. But I'm also interested, there's so many other 2D materials that people are also working with. So, how does it relate to other forms of graphene, like graphene oxide or reduced graphene oxide? And how do you think it relates to other two-dimensional materials?
Well, the AFM is very morphological, so it's like physical, right?
Yeah.
So if we have, is all a matter of sample preparation. You need a good dispersion to make AFM because things cannot be together. So this is very important. So it's a matter of sample preparation. If you have the sample preparation, the right sample preparation, which means flakes are separated, okay, and nicely deposited in a smooth surface, we can do everything we did here, okay? And we share our system, our automatic system with people, okay? So we have a lot of collaborators. Somebody just write and say, oh, I would like to try your system. We just share, okay? But it's a matter of sample preparation. If we have the right sample preparation, AFM is completely applied to everything. And we are starting with collaborations with other people. Claudia Bax in Europe, for example, she makes a lot of other type of liquid exfoliation materials. We have some interactions with her, people here local, and that we are expanding, okay, our system to these other types. And yes, so my answer is yes, everything can be expanded, but it's important to have sample preparation, the proper sample preparation. And this is important for the benchmark. So people do a lot of benchmark and talk about other people samples, but they don't show really how they prepare. And you cannot say, for example, if something that you cannot really nice disperse, the size of the thickness or something like this, this is very complicated. So you see that I didn't show any benchmark. I did a lot of benchmark. I didn't show because I'm not really like sure about how to prepare all samples in the world. This is very important. Everyone who makes their own sample has to work to make the right preparation for that system.
Yeah, no, I understand that. That's a discussion that's come up a lot, especially in the standards meetings that we've had. You know, the sample preparation is as important as any other aspect, and will greatly influence the outcomes. Even like doing the round robin tests, you know, it has to be prepared exactly the same, and even small deviations will give you a different outcome. Yeah, which is quite different. I have a different question for you, Luis, and we'll try to wrap up here because I know we've gone a little bit long, but the discussion is fascinating. We still have over 100 people listening to us. So the question I have is, you know, where next with this technique? Because I can see that this would have a really strong interest in the production environment. You didn't mention how long it takes to do these tests, but my understanding from before is that it's relatively quick process, you know, to do the analysis for the system. And you showed kind of an automated loop where, you know, you could get real-time measurement back, you can make an adjustment, so you have continuous monitoring. So my questions are, you know, if I'm a graphene producer and I want to use this in my production facility, how close is this to be, you know, licensed, commercialized? You know, how do people get access to this, and when do you think something like that might happen?
Okay, it's a good question. If you're talking about the AFM, I guess.
Well, you have this combination. Let me be clear, because
okay. So the circulating process.
Well, what I'm thinking of is you have combined AFM with Raman, and then doing mass sampling, and then the analysis. Okay, so a lot of this is in software. The equipment, I assume, is pretty much standard Raman and AFM. Is that right?
Yeah, that's right. So the Rama is a VTEC and the AFM is a PARC. The test, the nanoscope is not. That right. One is we built it.
But for your mass analysis and for this, you know, distribution, right, and for the surface area and for everything else, you know, to do that kind of, because what's very interesting is the sample size, right? I mean, how many flakes did you say you're measuring? 10,000?
10,000, 50,000.
Yeah, okay. So this is far higher than most people are measuring, right? So then statistically, you get a better representative sample. So is the magic in the software?
Mm-hmm.
Okay.
Is the software.
Okay.
I showed you the video. So it takes a blink,
Yeah.
just a blink. Okay. This is a really good work from the computer science people here. I know this is critical. I would suggest you to talk with Omar, which is my colleague from the computer science. And it's just a blink. We just take the image, load, and poof.
Okay.
That's the result. So this may be commercially available very soon, but we share with people. If you want to use it, we share. So we really want to spread this knowledge. So we understand that the graphene development, it has to be in a solid ground, okay?
Mhm.
So we want to provide information for people to compare, to measure, to understand the system. So this is a software, okay, which is locally developed, and we don't have a product yet that you go and buy or you
Yeah.
get license. This is like we build it here, okay, but we can share. We can show and share and explain and everything. There's no really secret, but it's a lot of work in the computer science. They did a really good job, and it's like a blink. Okay, everything is automatic.
So this is a really valuable tool, and I think you could offer this obviously as a service. You could offer it as a licensed product, et cetera. But what I think is most interesting is that it's relatively quick, and that it does a higher sample size, and it gives you more granular information. The last question I have for you, and I know that it's kind of built in as you guys have gone along. The biggest question that anybody might have is validity, right? And the uncertainty, how much uncertainty there is. So, you develop your mathematical models, your algorithms to do this analysis. But then how often have you been able to go back and validate and cross-check so that and for example, when we talked about, okay, what about graphene oxide? Do you have any reason to believe that you need to have a different algorithm for a different type of material?
Uh, yeah, this is a good question. Okay, this is a good question. Uh, uh, my guess is that we have to make adjustments. The grounds are the same, okay, but the small adjustments like okay, how the scanning probe interact with these systems. They have more surfactant or less. You have to improve the force, decrease the force. There are a lot of artifacts caused by the chemistry that is present there or
Mm.
not. So you may get roughness, which the system may think that is graphene, but is not.
Mm-hmm.
So yes, you're right. If you change the system, if you change the sample, you have to think, okay, about the artifacts, the uncertainties. I'm not saying that this is completely ready for everybody, like buy and use, and it will work, okay. But I think it's, as I said, we can expand this for pretty much everything.
Yeah.
But it's not like it's ready for everything. Okay, we have to think. You have like to adjust like the background of the AFM, the surface of the substrate. Everything matters. So
Right.
how the system knows that this is a monolayer and not a substrate? It's not a
Right.
surfactant. We thought
Well,
about this a lot in our system, but a different system may see different, may be different. So yeah, there are a lot of work to do, but we can do it.
well,
It's
I
just
think,
engineering.
yeah, I mean, you've already, probably done 90% of the foundation work that needs to be done, and then you can adjust. I think, for the audience and for anybody listening to this, I think the huge advantages with your approach are taking some of the human bias out of reading Raman curves, for example, because that's subject to human interpretation and you need to be trained to that. So you kind of automate that. And I think the much larger sample size gives you a statistically more relevant view of the material. And the other aspect that we covered that I think is quite important is this distribution based on surface area and mass, as opposed to a statistical number based on flake size, because of course, a nano graphite, is going to have many, many, many times more mass than a single layer flake of graphene. So are there any closing comments you want to make? And do you feel that the summation that I just gave, do you think those are the main points, or is there something else that we want to highlight?
Well, yeah, it just gave me a flashback here when we start with this project. As I said, I'm a Raman person. So since my beginning, I work with Raman. I watched all this development. And I want to tell a story. When we start with the pilot plant, with the first measurements, production, and so on, development, we had the Raman, but we did not have the AFM. So as a Raman person, everything that we measure was like by layer. I was like, sure, this is by layer, this is by layer, this is 4 layer. This is beautiful, okay? We make, everything is graphene. And we were very happy until the AFM came, okay? And we had like a specialist, very, very good specialist, okay? And he said, oh, this is not graphene. We have a lot of graphite here. And as a Raman person, I said, no, I'm sure this is graphene, okay?
Right.
I'm absolutely sure. And then he convinced me, okay, look at the images. This is not graphene, okay? And then we start all this fight, okay, to understand how they communicate, why Raman is so wrong, why AFM gives you something different. And then we realized that, oh, if you translate this for mass, this is really not graphene, okay?
Right.
And then we start to play with these things, and it's very rich. It's a rich subject, okay? And this is, I think, this is the main thing. Is just one technique is not enough. They communicate. We have to understand how they translate to each other, okay? And we have to try to make the largest amount of techniques together as possible. Each one gives you some kind of answer, and how to interpret the data, how to understand the system properly is not easy, is not done, okay? There's no Bible, okay, that you can just read and, okay, I know everything. We don't. As everything that is complex, as more you study, you get more answer, but the number of questions just go geometrically, okay? Yeah. So I don't want to say that it's very complicated, that we don't advance, that we don't know anything, but it's not that simple, that a simple spectrum just tells what is inside of a factory, okay? It's, we have to be reasonable.
Well, again, I want to thank you for sharing your work. I want to say congratulations to you and the team. Of course, there's a whole large team of people working behind you, both in the physics and in the computer lab, working on this. And we're also very excited to hear about this additional work that you'll be doing over the next year with some of these other techniques to cross-reference, which, ultimately we need things that are reliable and relatively quick and relatively inexpensive in the production setting. There were questions about, applications for graphene, and that's a different subject for a different day. And we have a lot of information from the Graphene Council. But the long story short is graphene is going to be adopted on a very large industrial scale, requiring hundreds of thousands of metric tons of this material. But if that's the case, there needs to be confidence that the material is what it says it is. And that's going to require these kind of mass measurement techniques that are easy to apply. So Luis, thank you so much. And thank you to MGgrafeno for being a member of the Graphene Council. And we're very happy to work with you to help share your work.
Thank you very much. Thank you for everybody who watched.
All right. Have a good day. Thank you. And with that, we're going to end today's webinar. Thank you everybody for attending, and thank you for being part of the Graphene Council community. Take care.